Hello and welcome. 18 months ago, I set out to learn about two game development related topics: tri-planar tessellated terrain shaders and running burst compiled jobs on parallel threads so that I can manipulate huge terrains and hundreds of thousands of objects on them without tanking the frames per second. I started off with combining tri-planar mapping and tessellation into a combined terrain shader, and then added height-based blending of various layers to create terrain that seamlessly combined different biomes and a variety of terrain detail. My shader reacts dynamically to groundwater, surface water, temperature, erosion, and slope that is sent through to the GPU in packed textures whenever any of these factors change on the terrain. But that's a topic for a different video. While developing the terrain shader, I also started looking into burst compiling and running jobs in parallel on threads. My first use case was allowing the real-time manipulation of terrain elevation. I needed a way to recalculate the vertices of the terrain mesh chunks as well as their normals, lightning fast. While the update call for each mesh can only be run on the main thread, preparing the updated mesh data could all be handled on parallel threads. But again, that's a topic for a different video. What we're concerned with today is how to populate this vast open terrain with all kinds of interesting objects, lots of them, eventually 10 million of them, in a way that our game still runs at a stable rate of more than 60 frames per second. Some of these objects will be only visual and static, but others need the added requirements of moving about and allowing player interactions. There are two main steps to solving this problem. The first step is figuring out which of the 10 million objects are currently visible to the camera, while the second step is actually rendering those visible objects. This video will consider the first step. For each visualized frame, we want to ignore the objects that aren't visible to the camera and only process the ones that are. This is known as Frustum Culling, since we check whether the objects are inside the camera's view frustum or not. I will provide a 40-second summary of this standard method before explaining how I've done something a bit different that allows me to get more out of the culling step. The camera's frustum looks like a flat-topped rectangular pyramid, with the base being the far clip plane, the top being the near clip plane, and the four sides connecting the base with the top, for a total of 6 planes. For each plane, we think of the side facing the center of the pyramid as the inside. An object will be visible to the camera if any part of it lies on the inside of all 6 planes. For each object, we have a bounding box or bounds completely containing the object, and we can perform a set of calculations to determine whether any part of the bounding box lies on the inside of all 6 planes. However, I've done this step in a slightly different way that allows me to also determine whether the object is currently under the mouse cursor on the 2D screen or inside a rectangular selection box on the 2D screen, all while performing the culling and without using colliders. I also gather some other useful information during this step, more detail a bit later on. Either way, performing these calculations for hundreds of thousands of objects start eating into available CPU capacity, especially if it runs on the main thread. Now, Unity has been performing Frustum Culling on parallel worker threads for a while now, so why would I be interested in performing this myself? Firstly, I wanted to learn and found the process fascinating. Secondly, while allowing Unity to handle the behind-the-scenes work for you automatically can have its benefits, there can also be unnecessary overhead involved. A bespoke solution taking the specific situation into account can be more performant than a generic solution, even if it takes longer to implement. Thirdly, the more you understand, the more control you have, the more you can squeeze out of every required step to improve another dependent step in the process. Additionally, the rest of the game will include a lot of burst compiled jobs on parallel threads to allow the player interactions and game mechanics to run smoothly, so the managing of objects need to be aligned with the rest of the game. So how did I go about getting my terrain populated with 10 million objects? First off, there was no way I was going to create an actual Unity game object, with all the overhead for each world object. I would simply have to manage all the data and memory usage manually, and that's where native memory, burst compiler, and parallel jobs come into play. When I started looking into Unity's jobs system and the burst compiler, it was clear that the gains from using these would be extensive, especially in my use case. However, there was something that kept bothering me. In the examples I'd seen, each time before each job was scheduled, you had to reserve new native memory and populate the native memory used in the jobs from the managed memory the rest of the code uses. Then, after the job had completed, you had to populate the managed memory from the resultant native memory again. This is probably fine for small examples, but when the number of elements go to hundreds of thousands, I couldn't see this being viable. Then I thought, why have two versions of the data, native and managed? Why not just use persistent native memory throughout? Sure, it's a bit of a hassle because you have to have fixed lengths or capacities for native memory and have to reassign when you want to change these, but with a bit of management you can limit these occurrences to very few and far between. Also, you can really mess up if you don't handle native memory properly, but after a while this also becomes second nature. And there are a lot of safety checks that warn you of dangerous or unsafe use. Probably the largest performance gain from jobs, other than allowing more than one thread to perform the calculations and the optimizations of the burst compiler, is due to the native memory used being in contiguous blocks, whereas managed memory can be scattered around. This means that large chunks of memory can be accessed at a time and worked through, where you have to jump around a lot more when working with managed memory. This greatly reduces the time required to read from and write to memory in jobs. Many programmers are used to an object-oriented data structure design, where the packet of information for an element in the list is grouped together, and the list contains a collection of these packets. In this case, probably the biggest adjustment we need to make to our data structure design when using jobs is to switch to a data-oriented design. Jobs require native arrays or native lists containing structs, not classes, since it needs to know exactly how much fixed memory each element takes up in the block of native memory. The fixed size of the struct allows it to jump to the exact location of that element's position in the native memory block. We could create a struct containing all the information for an element, and then a native list of these structs. But the entire struct then needs to be read or written even when only one of the elements is required, or needs to change. For this reason, we rather create a native list for each variable that would have been part of the struct. There are actually a few more bits of information required, for example to link each entry back to the actual mesh and material it represents. But I've simplified it here to clarify the main idea. Now, as we add visual elements to our terrain, we add their data into the Visual Manager's native memory, leaving us with native lists filled with all the information we need to perform the culling for each of the elements. We now have to create a job to handle the culling, then send this data as well as information about the current camera view to the job. Let's first look at the less complex task of creating an instance of the job and populating or linking its data, before we go into the more complex detail of the job itself. When creating an instance of a job, we need to ensure that we populate all of the external data it requires to work. These are defined in the job, which we'll have a look at soon. We only need to link the native lists to their counterparts in the job once, unless we possibly dispose and reassign them in the future. So we link them when creating the job. On the other hand, some data could change every frame, so we update these every time they change. For example, the camera's view and the position of the mouse cursor. We then schedule the job and wait for it to complete. If there are tasks that could run on the main thread while waiting for the culling to be completed on the worker threads, the complete call can be moved to after those tasks have finished. As long as those tasks do not make use of the native lists the job will be impacting. So what exactly happens in the job? Firstly, we define the visuals information and the camera information. Note that we can specify parameters as being read-only and write-only. We can also relax safety checks to allow a thread to write to a different index than the index it is currently processing. This is needed because every index in the positions array takes up 8 entries in the bounds 8 points array, namely the 8 corner points of the bounding box. As long as we are certain that different threads would not try to alter the same index, which we are here, we can safely relax the safety check, allowing a thread to access all 8 of the points corresponding to the index it is currently processing. Another important and useful thing to notice is that you have access to the index of the current thread processing the element. This allows us to write out summary information per thread into specially creative native arrays with an entry reserved for each thread. Outside of the job, we can then collate and use that information as we see fit. In this example, each thread would determine which of the elements it processed was the closest to the mouse cursor, if one or more indeed were. Outside of the job, we consider these candidates and pick the one that was the closest overall. Additionally, note how we also define a set of parameters that allows us to determine on which terrain chunk an element is situated. If that terrain chunk is not currently visible, we can quickly discard that element without having to perform costly checks. Finally, a collection of private temporary variables completes the parameter definition. All that remains now is to perform the actual culling and to determine whether the mouse cursor is hovering over an element, as well as which elements are within the mouse selection rectangle while we're at it. We do this by mapping each of the relevant points in 3D world space onto a 2D screen space, as it is displayed. In essence, this is similar to determining whether any part of the bounding box is within the frustum, although we convert the 8 corner points to points on the 2D viewport of the camera. If a converted point lies within the 0 to 1 range of the X and Y axes of the viewport, it falls within the visible part of that plane. We add a small margin around this to allow elements on the edge to still create shadows. Then we also use these converted points to determine whether the current mouse position is over the bounding box, and whether the bounding box falls within the selection rectangle, allowing the selection of multiple elements at once. Now, running this on my CPU easily gets me up to 1.5 million elements processed per frame, but there's something more we can do to improve performance. A huge percentage of the displayed elements are only cosmetic, stay in place, and do not require individual interaction other than being placed and removed. I already have a hex grid system consisting of up to 160,000 hexes underlying the terrain, and many small visual elements are assured to be constrained to a communal bounding box around the hex they are situated on. This means I could calculate the visibility of the bounding box of each hex once off, then just look up the result of the corresponding hex for any of these constrained cosmetic elements, rather than repeating the more costly calculations for each of them. This does mean I send a few unnecessary elements right on the edge of the view to the GPU to be rendered, but the gain in culling performance allows up to 10 million elements, most of them cosmetic, to be scattered across the huge terrain. As long as only reasonable amounts of the different types of elements are actually visible at any point in time, the game still runs smoothly at over 60 frames per second, since the culling happens so quickly. And that's it for this video. Please let me know in the comments which technical areas you would like more detail about, and subscribe to this channel, wishlist and follow Minor Deity on Steam, or join the Discord channel to stay up to date. All the links are down below. Also feel free to ask specific questions you may have. Thanks for your time and support.